Okay, so this will be about the reaction rate and reactant concentrations. Okay, so let's start off with the first order reaction. Okay, so suppose we have A becoming a product B, right? And we know, okay, suppose from experimental data that the rate equation is given by rate equals to K times the concentration of A. So this thing we can actually graph it, right? Okay, so if we have like a y equals to mx plus c curve, okay, so y is the rate if we have the y as the rate, okay, and mx, so x is concentration of A if we plot against that, so m would be the K, and C is kind of like a plus 0, right? So it will pass through the origin and it will have gradient of m, right, which is gradient of K, so the gradient is K. Now we also know that from math and everything, okay, that if we plot, if the rate, right, rate is dA over dt, if dA over dt is proportionate to A, okay, then we'll get this graph, okay, such that the half-life is a constant. So half-life is, okay, let's say the concentration started at 10. Half-life is from 10, how to get to 5, or 5 to get to 2.5, right? And we know that this has to be a constant, right? If it's a first order reaction, this T half is the same as this T half. And that's how you test whether something is first order or not. It's by checking the half-lives. So if the half-life from 10 to 5 is the same as this, then we can conclude that it is first order with respect to A. Okay, so that's how you check. But what about a product time graph, right? So let's say your product is B. Okay, so we know that if we draw a BT graph, how do you conclude a half-life from here? Okay, let's say this is T. Okay, sorry for the not labeling. Okay, we know that A goes to B. So when A is 10, okay, we just plug in some numbers, okay? When A is 10, okay, B is 0, right? When A is 7.5, B is 2.5. When A is 5, B is 5. When A is 2.5, B is 7.5, right? And when A is 0 finally, B is 10. So if we plot a graph, right, we actually note that B is the same as 10 minus A, right, or the concentration, okay. Concentration of B is the 10 minus concentration of A. So if we draw a 10 here, and a minus, if we do the math, we'll flip it like that, right? So what's the half-life? The half-life is from A to get from 10 to 5. So in this case, it's from B to get from 0 to 5. Okay, so we have a 5 here. So this half-life, T half, okay. Then we also know that the half-life is from A to get from 5 to 2.5, which is from B to get from 5 to 7.5, right? So we have to mark out 7.5 here. Okay, and I know this is not proportionate, but we have to assume that this half-lives, if they are equal, then it is first order with respect to A. So what you have to notice here is that when I'm actually counting the half-lives, okay, from 0 to 5 to 7.5, suppose I have to draw a product time graph, okay, and I'm plotting a product time graph and I want to see whether it is first order or second order or third order, okay, and I note that the half-life that I have to calculate has nothing to do with dividing into half. Do you realize? It has nothing to do with 0 to 5 is not dividing by half, 5 to 7.5 is also not dividing by half, right? Okay, the reason why is because the half-life is for the reactant to be divided by half, not the product. So from 10 to 5, the product 0 to 5 has nothing to do with half, right? So for this, we must know what V infinity is, or what this initial A or the final B that I will get is. Okay, and then from here I can calculate B equals to 10 minus A. So the first half-life is really for the product to get from 0 all the way to 10 divided by 2. Okay, and then after that the second half-life is, okay, this is 10 divided by 2. the second half-life is to get from 10 divided by 2 to 10 divided by 2 plus 10 divided by 4. Why is that so? Because, okay, this is the second half-life, this is the first half-life. Because at the first half-life is when A becomes 5, or when A divides by 2. So the product that you will form is the total number of product that you will form in the end divided by 2. So from 0 all the way to 10 divided by 2. And now that I have already formed 10 over 2, the next half-life would be from how I get from 5 to 2.5, right? Where I get from my reactants, 1/4 of the total reactants are reacted, right? So if 1/4 of the total reactants are reacted, then this is the amount reacted already plus 1/4 of the total reactants reacted, which is 2.5, and so that's 7.5. So that's how I would calculate the half-life if I'm given a product time graph and not a divide by 2 or times 2. But the important thing is that I have to know what this is, right? Because if I don't know what this is, if this is a question mark, how do I know to get to 5? How do I know to get to 7.5, right? Because it's question mark divided by 2, or question mark divided by 2 plus question mark divided by 4. Okay, so that's the basic idea of the first order reactions. Okay, so now of course let's look at the second order and zero order. This one is less common, okay, and it will come out less, but we'll just have a look. Okay, of course, wait, sorry, before that I have to know that half-life and k is related. Okay, t half is ln 2 divided by k. This means that if I have t half, I can calculate k. If I have k, I can calculate t half. This is always a constant. Okay, so if suppose that from the graph I can calculate k, okay, calculate t half, sorry, I would know that I'll be able to calculate k, right? And I'll be able to calculate k, and that would be useful also, because sometimes, let's say I want to ask for the initial rate. So if I ask for the initial rate based on the graph, I know that rate is given by k of, let's say, a, right? Okay, so if I know t half, I will know k, and I can find a maybe from the graph. So I plug in the two values and I'll be able to find the initial rate. Okay, so there's a sort of an equivalent in a sense for first order reactions only, of if I know t half, I can find k, if I know k, I can find t half. So if I know one, I'll know the other. Okay, so now let's go on to a zero order and second order. So zero order is basically saying that your rate is just equals to k. It's not dependent on the concentrations at all. So if I draw a rate with a graph, okay, what I'll get is independent. Okay, this value is k, so the value is k. Rate equals to k. Okay, it's just drawing a simple graph. So if the rate, or dA over dt, is a constant, and we know that the gradient of a AT graph, okay, which is dA over dt, right? The gradient has to be a constant. Okay, so if the gradient is a constant, this gradient is given by k, because dA over dt is k, right? Because that's the rate, dA over dt is k. And also we note that half-life is not constant, because if it's like that, half to get this, okay, it's quite obvious that it's not constant. This is half of this, okay, because it's a straight line graph. So if we graph a product against time, remember product b, okay, suppose that this is 10, right? This is 5, 2.5. B, or the concentration of B is 10 minus the concentration of A from above. So if we draw 10 minus A, if we graph it, okay, and there's no space on screen, it's like that. And the gradient likewise is also k. Or in this case, sorry, the gradient is negative k. This gradient is k, because rate is like negative dA over dt. Okay, so that's for zero order. How about for second order? Second order, okay, it's given by, okay, sorry, let me go down. By rate equals to k a squared. Correct? So if I draw rate against a, okay, rate against a, what will I get? If it helps, you always do the math way, right? Y equals to kx squared. So what is y against x? Okay, is quite straightforward, right? That is just a curve like that. It's a quadratic curve, where if this is A, okay, at this point, and this is R at this point, then the next point here at 2A, we will get 4R because it's a quadratic curve, right? So this one is like 1, 2, and then it's 1, 4 because Ka squared. How about graph of rate against reactance squared? Okay, I'm just explaining all the graphs here. Rate against reactance squared, or A squared. Okay, so A squared is the variable. So what y equals to rate equals to K of A squared. So it's a straight line. And of course, reactant against time, we will know that it's not a constant half-life. Okay, and in fact, the half-life of the second half-life is twice more than the first half-life. Okay, the derivation and everything will not go through, but just remember that if it's A over T, the second half-life is just not constant, okay, or it's double the first half-life. Okay, so what about now we'll go on to pseudo order reactions. So suppose that we have a reaction like A. Okay, the rate actually here is given by K of A and B. Okay, suppose A and B become C. Okay, the reaction is like that. A plus B becomes C, or C plus D. Okay, so if we know that the rate equals to KAB, okay, and A, concentration of A is so much greater than the concentration of B. Okay, I've exaggerated it a bit. If we look at the table here, let's say T equals to 0, okay, concentration of A is 1, but concentration of B is 0.00002, right? So the rate, assuming K is 1, okay, is actually 0.0002, okay, if K is 1. I'm just giving an arbitrary number, just for the sake of explaining. But when T equals to 1, okay, suppose that this decreases by half, right, and this decreases 0.0001. What happens to A? A decreases also by the same amount, right? Because of the Stoichiometric equation. So it's 1 minus 0.001. So rate, in a sense, is K, which is 1, okay, times 1 minus 0.00001 times 0.00001. Can we see that this is about 1? If we have it to like 3SF, this is about 1, right? So the rate is still 0.00001. Okay, so we can see here, actually I use Excel here, right? And they actually approximate 1 times 10 to the power negative 5, which is 0.00001. So because this is about 1, we can do an approximation, and we say that even when B totally diminishes, okay, to 0, what happens? The rate sort of becomes 0, but A is still like 0.99998. So it's really about the same throughout the whole reaction. The concentration of A is almost constant, okay, throughout the whole reaction, because B is so small, right? So even if B totally diminishes and you react all of the B with A, there's still that so much amount of A that it doesn't really matter, right? So if this is a constant and this is a constant, it is sort of like rate equals to K prime of B, because A is a constant now, or we say that it doesn't change throughout the whole experiment, where K prime is K times the concentration of A. Now, because K prime is still K times concentration of A, if I times it by 2, the rate, or if I times A by 2, the rate will still actually increase, right? So I'll give you an example. Let's say A now is 2, okay, and B is still 0.00002, right? The rate in this sense, if we compare it with this, is actually 0.00004. So the rate changes. So even though rate equals to K prime times B, this is saying that as time goes by, okay, the reaction acts like a first order reaction with respect to B, because A effectively remains the same, 2, and after that 1.999999, and this one built 0.00001. But it does not mean that the rate is independent of A. We have to understand that if I double it by 2, the rate is 0.0004, and comparing with this, the rate actually changes. It's just that over time, the rate only changes with B because A remains constant over time. But you still have to remember that K prime is still K times the concentration of A in this sense. Okay, that's a very important thing that we have to take note of. So, if I just want to compare this, okay? Okay, let me, okay, yeah, with something what if it's not, what if this is not true, right? What if A is roughly about B? Okay, then we see that if A is roughly about B, let's say 1 and 1. Okay, so the rate, I'm assuming K is 1, it's just 1. But when B decreases by 0.5, we know that A has to be consumed also by 0.5, right? So if this is not so much more than this, looking at the numbers here, we know that this is very significant, right? So it's 0.25. Now, how can we say that rate equals to K prime B, okay, if B decreases by half, but the rate decreases by 4 times, correct? But in this case, B decreases by half, but the rate effectively decreases by 2 times, decreases by a factor of half as well, right? So this one we can say that rate equals to K prime over B, but this, because A is not so much more than B, we cannot say it, right? Because A is kind of being reacted, or A does not remain effectively constant even as B changes. Okay, hope that makes sense. If that doesn't make sense, you can always ask me again. So if we draw a graph, okay, of concentration of B for the first reaction where A is so much bigger than, okay, where A is so much bigger than B, right? We'll get a first order reaction. Okay, because rate equals to K prime of B. So in a sense that the K is a constant, so it only the rate, or dB over dt, only depends on the concentration of B. Okay, but what if, let's say, just for fun, I want to draw the concentration of A? Okay, because in this case, right, it starts off with 1, and in the end it kind of ends off, right, if this is 0, when this reaches 0 at a complete reaction, 0.99998. Okay, and suppose that this is 0, okay, and 0.9998 is over like here. Actually, it's almost 1. So the rate, even though it may follow somewhat of a curve, but if we look at it, it's kind of constant because 0.99998 is just over here. Correct? So, but for B, it's starting from 0.00001 or 0.0002. So when it drops by 0.001, okay, for A it doesn't make a difference, but for B it makes a huge difference. It's a factor of half. Okay, and that's why it follows a first order reaction, and then we go on, and it's like T half. Okay, but like I said, if I want to illustrate this point, that it's still dependent on A. The rate equation is still rate equals to K of A and of B. Okay, then I would say that if I change A, okay, so I'm changing K prime because K prime equals to K of A, right? So if I change A to 2, okay, what will happen? My graph will still follow a first order reaction with respect to B, but it will be like that. Okay, and it will, okay, suppose that I continue drawing. So you note that the initial rate, okay, the initial rate, or the rate at this point of time, is given by rate equals to K of A and of B, right? So B always started at 0.0002. But for the first reaction, okay, or for the second reaction, A is 2 now, and K I'm assuming is 1. Okay, compare that with the first reaction where you had 1 times A, which was 1, and 0.00002. So the rate actually doubles at this point of time, right? So if the rate doubles, we know that the instantaneous rate, or the gradient of the graph, okay, for here must be twice as steep, because the rate at this point is double the rate at this point. And what does this have to do with half-life as well? Okay, we know that T half equals to ln 2 over K. Now, because I say that the rate effectively for this is rate equals to k prime over b, t half is ln 2 over k prime, or ln 2 k times the concentration of A. Okay, so if somehow my concentration of A changes, okay, or it doubles, okay, so for this purpley reaction, or the second reaction, t half equals to ln 2 over k times 2. But for the first reaction, which is the blue reaction, t half equals to ln 2 times k of 1. So the t halves are different also. Okay, so you have to know that it's a pseudo order reaction in terms of B, but it's still dependent on A. And a pseudo order reaction helps me in that, because if it's in excess and the graph of B against T, it's kind of like a first order reaction because A remains the same, right, over here. Then I can check if it's a t half, if the t halves are the same. Now if the t halves are the same, then we know that it's first order with respect to B. But if the t halves are not the same, or if the t halves are not the same, and maybe the second t half is more than the first, double the first t half, then maybe second order. But usually it's the same for A levels. Usually they test all the same. Okay, and if I want to know the order of reaction with respect to A, then I have to draw another graph with a different A, or different concentration of A, and then I see how the instantaneous rate at this point changes. If it doubles, if the instantaneous rate or the gradient, okay, because the gradient is dB over dt, right, or the rate. So if the gradient doubles, and when A doubles, then we know that's first order. If the gradient multiplies by a factor of 4 when A doubles, then we know that the reaction with, or the rate equation has rate equals to k A squared. Okay, make sense? Okay, so we know that in this case we can approximate this. So what other cases can we approximate for pseudo first order? If the solvent is a reactant. Okay, so suppose like we have an example given by the lecture notes here, which is CH3COO CH2CH3 plus H2O is the hydrolysis of an ester, becomes CH3COOH plus CH3CH2OH. Okay, so the rate equation actually is given by this. Okay, we know that rate equals to K times CH3 whole ester times H2O. But because water is a solvent, right, and because water is a solvent, it is present in large excess. So the fact that it's large excess means that H2O is so much bigger than this CH3COO CH2 CH3, and essentially is like above like the same, right, for A and B. If one is in much large excess than the other, this remains effectively constant throughout the experiment, because even if this decreases to 0, this is still about there, about the same, right? It doesn't decrease by that much of a factor. So the rate can be modified into rate equals to k prime of your CH3, blah 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 blah, right? But we have to know that k prime is still k times H2O. It's just that it seems like it's this because this remains effectively constant. Now what if it's a catalyst? Also same thing. But this time we're not using this argument, but we're saying that it does remain constant no matter what, because the catalyst is regenerated. It has to remain constant, right? Because you won't use it up in the reactants. But that is so. For example, okay, let's give a lecture notes example. Wait, let me copy it. Let me use a snipping tool. Okay, so given this lecture notes example, we say HCl is the catalyst, and then after that we say that the rate experimentally found is this: rate equals to K times HCl times sucrose. But because HCl is a catalyst, this remains effectively constant, so it's still K prime times sucrose, right? So if I draw a graph of sucrose against time, I would still get a first order with constant T half like this. But if I change my concentration of HCl, so if I double my concentration of HCl, I will still get a first order graph, but my gradient will be different, my half-life will be different because of this. So all the pseudo first orders are just saying this. It may be overall second order, and it may be dependent on the concentration of A. But with respect to time, the concentration of this will follow a pseudo first order in that it will have a constant half-life. But the HCl here, or the catalyst, or even A here, the concentration of A, will also affect it. It's just that it doesn't show that it decreases over time, and it doesn't show that it affects it over time because it's effectively constant. But if I double the initial concentration, then the initial rate will also change likewise.